Thanks a lot for giving me the opportunity to speak here. I've had a lot of fun learning about all these different aspects of topological and geometric aspects of computer science. Okay, so today I'm going to talk about efforts to extend homotopy type theory to encompass kind of directed phenomena. And since I don't see many experts in the audience, this will be fairly much of an introduction, kind of continuing Eric's introduction that we saw yesterday. Okay. So first I'm going to kind of continue introducing homotopy type theory, not just homotopy theory, homotopy type theory and homotopy theory via type theory, and kind of particular draw out the aspects that I want to change and to make into a directed version. And then I'm going to talk about the requirements that we want for directed type theory. And then I think at the end I'll just have a little bit of time left to say something technical about what has been done so far. Okay, so the moral of this first section, which is about homotopy type theory, is that not only can types represent spaces, which Eric did a great job of explaining yesterday, but homotopy type theory is the right setting in which to do homotopy theory, or to do mathematics topically. And this is because everything we can say or do respects equality or identity, two different names for the same thing. And with the homotopical perspective on type theory, aka homotopy type theory, homotopy in terms of the identity type. Okay, so in the next slide, I'm going to kind of explain what I mean by this. Okay, so let me explain a little bit about how we get infinity groupoids of types, or how we see that types are infinity groupoids. So as Eric explained yesterday, I'm going to try to be consistent with the coloring that you use. We have, when we, in the type theory, the identity type is defined with 4 rules. And we have these first 2 rules. The first one just says that for any type A and for any 2 terms in the type, we have an identity type. And we think of the terms of this guy as proofs that A is equal or identical to B. And we have an introduction rule telling us our favorite proofs of identity, which is that if we have a type A and we have a particular term inside of A, then there's a canonical proof that A is the same as A. Okay, so as Eric also explained, we get a tower then of identity types and in terms of identity type. So if we have a type, now we're going to think about it as a space. We have a type with terms in it, like points. Then we have between any 2 points a type of identities. There might be multiple ones. And between any 2 identities, P and Q, between A and B, we might have a whole identity type there. So it might be higher identities or paths, and so on and so forth. We have points, we have terms, what do you think of as points? We have 1-dimensional paths, 2-dimensional paths, 3-dimensional paths, and so on and so forth. And that's just what we get from the formation rule. And the introduction rule tells us that we have these canonical terms at every level, telling us that we take the same guy twice is equal to itself, of course. Okay, so we have something that looks like an infinity category with identities, identity morphisms. Okay, so I want to explain now how we actually get something that really looks like an infinity groupoid, how we get, say, composition and invertibility. And for this, I want to actually get a little bit more into the type theory. So I want to motivate this by describing how the Booleans and the natural numbers are defined in the type theory. Okay, so the Booleans, so we're just thinking of this as being something like the set of true and false, or 0, 1, as I plotted here. So we have the first 2 rules, just like the identity type. Without any hypotheses, we just have a type of Booleans. And without any hypotheses, we have 2 terms, 0 and 1. So we get 1 type B with 2 canonical terms, 0 and 1. And now I want to explain like this rule, or these 2 rules actually, that govern the behavior of the Booleans. And I'm going to kind of use this to bootstrap into an understanding of how the identity type behaves. Okay, so how do the Booleans actually behave? And maybe one way to understand this is if we think of this as a proof system, we have here rules for how to prove the Booleans or how to produce an element of the Booleans. And this rule is telling us how to use Booleans or how to use a term. Okay, so if we have some type dependent on the Booleans, I think for this, it's going to, especially when we get to natural numbers, it's going to make a lot of sense to think of this type as really being a proposition about, like that we can plug in 0 here and get a proposition about 0, and 1 get a proposition about 1. So we've got an index proposition over the term 0 and 1 of the Booleans. And this rule is telling us how to prove that that proposition is true for all terms of the Booleans. Okay, so what it's saying is that if we have such a proposition that we want to prove is always true, if we have a proof that is true for 0, and a proof that is true for 1, then we can put this together and have a proof that is true for any x in the Booleans. Okay, so like that's pretty obvious, right? Like that's what you would expect. That's what you would expect it to mean to prove that something is true about 0, 1. Because proof is true for 0, proof is true for 1, you're done. And these two rules here, so we call this the elimination rule, this is the propagation rule, when anyone's interested in the names. And these rules just say that if we plug in 0, 1, we get back the original proofs that we put into the machine. Okay, so maybe the punchline is that the behavior of the Booleans, like how we can use the Booleans or prove things about the Booleans, is determined at the canonical terms. So we just have to do this, whatever we want to do at the canonical terms, and it's true everywhere. And yeah, I mean, we can think that in some sense it's saying that the Booleans just have the two terms 0 and 1. Indeed, they do. Okay, so the natural numbers is very similar, but a bit more complicated. So again, we have this rule that says that without any hypotheses, we just have a type called the natural numbers. We have the introduction rule, which says that without any hypotheses, we have one special term, 0. And if we have another term, n, in the natural numbers, then we have a further term, the successor of n. And we're generating the natural numbers like this. And again, we're getting one type with these canonical terms, 0 and all the successors. And then we want to know how to use the natural numbers, like not just get terms of the natural numbers, but use the natural numbers, prove things about the natural numbers. And we have a similar rule as we did in the Booleans. So if we have some type index over the natural numbers, and now I think it will especially make a lot of sense to think about this as a proposition index over the natural numbers. Right, we're going to be doing some induction here. If we have some proposition for each natural number, what do we need to prove that this is true for every natural number? Well, of course, it's going to be an induction principle, right? This is a mathematical principle of induction. So the rule telling us that if we have such a proposition about every natural number, and we have a proof that it's true at 0, and for every natural number x, and every proof that the proposition is true at x, if we have some operation, let's say sigma, that turns that proof that the proposition is true at x into a proposition that the proof is true at the successor of x, then we can put all that together and get a proof here that the proposition is true just at any x and n. Okay, so just the normal mathematical principle of induction. It's true at 0, and you can turn a proof that is true at n into a proof that is true at n plus 1, then you have that is true at all natural numbers. Okay, and again, these two rules are just saying that if we plug in this information that we started with, we get back the same proofs. Okay, so again, the behavior is determined at the canonical terms, at 0 and at the successors. Okay, does anybody have any questions about that? Okay, so I hope that made sense. So now I can use that to explain the rules for the identity type. And what's so unusual, I think, about the identity type and what makes it behave like homotopy is that we're defining, or Martin-Löf defined quality, the identity type, in an inductive way, just like we define the Booleans and the natural numbers. It's kind of strange in the history of mathematics, look what we did. Okay, so we already saw the rules that introduce the identity types and introduce the canonical terms reflexivity. And now we want to see how to use the identity type or prove things about the identity type. So there's going to be a kind of induction principle here, like there was for Booleans and natural numbers. And so this principle says that if we have any two terms, x and y of a, and really what we're really interested in is just like an arbitrary path or an arbitrary identity. I'm going to probably use the words equality, identity, path, and homotopy interchangeably. If we have some arbitrary path z through points x and y, and over all that kind of stuff, we have some proposition that's indexed. So we're trying to prove something about the paths. And we want to actually inhabit this proposition. We actually want to produce a proof that it's true for every path z between every 2 points, every 2 terms x and y. Then the just like for the natural numbers and the Booleans, we only have to show that it's true at the canonical terms. So we only have to produce here, the second line is saying we only have to produce a proof that this proposition is true at the reflexivity term at any point. So if we can prove that something is true at the reflexivity or the kind of identity or constant path, then it's true at all paths. Right? Again, we have this computation that will explain us that we don't get anything that more than we started with, really. Okay, and now we can see, I think maybe I've used up all my license to be super technical, so I'm gonna maybe prove some things now just in words, but of course the proofs really, and even the statements, maybe should be translated into symbols like we see up here to be really rigorous. But we can use this rule now to prove lots of interesting things, and in particular, prove that every type has a structure of an infinity group, right? So we're missing was decomposition and invertibility, at least to start with. Okay, so we can easily prove that every identity has an inverse. Every term of the identity type has an inverse. And how do you do this? I'm not going to write any symbols. I'm just going to now kind of use this rule in words. You just have to prove that every reflexivity identity has an inverse, right? And we can just choose the inverse that we want, and we can just choose itself. Okay. So since when we restrict to the reflexivity identities, the statement is trivial, then it's just true at all paths. And similarly, if we want to produce a composition function for any p from x to y and any q from y to z, then the proof is, again, just by induction, we can assume that one of these is reflexivity. And since it's true there, we can just say that the composition of p and the reflexivity term at y is, we just want it to be p itself. Since we have a candidate there, then that produces composition for any p and any q. Okay, and so we can also make similar proofs saying that, like, if we compose a path and its inverse, then that's identical to the reflexivity identity at the starting point and all those kinds of concurrencies. And we find that every type has a structure of infinity. Okay, maybe I should ask any questions about this, about group weights. Okay, so now I want to start talking about not just infinity groupoids, but maybe abstract homotopy theory and how we don't just see that each type by itself has the structure of an infinity groupoid or a space, but really that these rules, the rules for the identity type, make it so that the whole collection of types behaves to some extent like a Boolean model structure, really some particular kind of weak factorization systems. Okay, so the important thing here in this whole talk is really going to be transport. It's called transport and homotopy type theory. And so I think the statement of transport is maybe this first sentence. Given any dependent type D on any other type A, and any path here from, say, an X to a Y, we can kind of elevate this path P to a function between this type D of X and D of Y. So we can, if we think of, now, as I explained in the past slide, we think of the paths as one cells and the infinity groupoid A, then what we're saying here is that this kind of thing is functorial, at least in the one cells. Okay, and maybe we can make this match up with our homotopical intuition about I don't know, vector fibrations. This P star we can show is an equivalence, and there's an identity, like a path from P, if we take any particular guy, little p, in D of x, and and apply this lifted function from D of x to D of y, we get a path between those two guys. Okay, and so again, we can easily prove this using our principle of induction for the identity types by just considering the statement not at any p, but at a reflexivity term and a trivial. Okay, but I want to compare this now. I'm going to start talking a little bit more about homotopy theories. So I want to compare this to situation maybe in topological spaces. So I want to now start arguing that dependent terms, if we have, or dependent types, if we have something like a type D of x dependent on A, that behaves like a fibration. We're going to go to this example of Paretov's fibration. Okay, so we can think about this this bundle of information. Maybe I can use the mouse here, so I'm trying to point up there. This bundle of information here, we can represent it as Eric did, as not something that looks like a function out of A, but we can kind of bundle up all the D's and think about the projection of that union or that bundle down to the indexing type A here. So we can think about this more in this format, where we kind of take the union of all the D's and think about the projection to A. Okay, so in maybe topological spaces, we might be used to thinking about fibrations, Horayevitz fibrations, as guys which, well, in particular, if we look at some particular space here, like the interval that has two specified points and a homotopy between them, and the inclusion into, say, 0, and we construct a diagram like this, then we have a lift of this interval. So if we have some path in A and a lift of the starting point, then we can lift the whole path. Okay. And you can indeed bootstrap this. I think this is a lot less than being a Horayevitz fibration. If we really write down the definition of being a Horayevitz fibration, suppose there are different ways to do it, but this is one way where we consider, say, something like a path object in the model structure. So we could think about something like A to the I, that would be like gamma A, more paths, but something like A to the I here for path A. And then a Horayevitz fibration is something for which, if you take the mapping path space factorization of this orphism pi, then you get a lift. Okay, so what is this actually saying? So this space here is really, so now it's talking about topological spaces. This space here consists of pairs of a point in D and a path in A that starts at the projection of the point in D. So it indeed is like a path in A together with a lift of the guy C. And asking for a lift here is saying that we can lift this path in a truly functorial way. Maybe there's a little bit of algebra to do here, but if we're used to the theory of model structures, or maybe just the situation in topological spaces, we know that we can extend this, well, first of all, to a function from, say, we have a particular path in A that we're interested in. We can use this information to produce a function from the fiber over the first point to the fiber of the second point. So paths in the base space produce functions in the total space. And indeed, we can show this as a homotopy equivalence. Okay, so we have exactly the same situation going on in, say, topological spaces or any situation that looks like this as we do in type theory. Okay, so I want to make the point that I guess the rules for the identity type are a little bit stronger than transport, but really boil it down to this notion of transport as kind of the most important consequence. And that is really just a kind of notion of being a fibration, of being able to lift paths, or in particular, produce, take a path to a function of fibers in the total space. Okay, so to say this a little bit more technically, let's suppose that we're in a finitely complete category. I want to talk about this notion of fibration just in categories with homotopy theories a little bit. It's a theorem that identity types can be interpreted in any weak factorization system in C, such that, first of all, it's the weak factorization system is generated by a path object, and two, it's symmetric. So let me say a little bit about what that means. So condition one is saying that there is some path object like this in the category. So for example, we could take, if we're in a super nice category, usual, we could just take x to the I if we have some kind of cylinder I, or interval I should say. Or maybe in other categories, we could do something very, very similar to taking x to the I for path x. And this morphism, of course, takes like a point in x to the constant path, and this projects to the first and last points. Okay, and then we're just gonna say this started really quickly. Hopefully some people know what I mean. So we have this path object. We can factor any map using the mapping path factorization given by this path object, and that we can ask if that produces a weak factorization system. If it does produce this weak factorization system, then we're happy that one is satisfied. Okay, so here path x is going to play in this correspondence between identity types and path objects. Path x is playing the role of the whole union, the whole sigma type of these individual identity types. So here we have like all the paths in x, and in these guys we have just the paths from x to y, so we bundle them up. And R is of course playing the role of reflexivity. Okay, and then two, the fact that the weak factorization system is symmetric means that there is an involution, in particular on this path space, that preserves reflexivity terms, or makes this triangle commute, and switches, here this epsilon 0 to epsilon 1, switches the endpoints. Okay, satisfying some properties. So I am hopefully now kind of foreshadowing the idea of directed homotopy type theory, which is that we want it to correspond to having a path object in the category, but not to having an involution, not to having a symmetry on those paths. Okay, so here are some basic examples, maybe your favorite examples. So in any category, we could take the path space to be either x itself, that's the minimal option, or x times x, the maximal option. So when we take it to be x, this is representing literal equality in the category. And so we might say this is a model of extensional type theory, for those of you who know what that means. And when we consider x times x, and we're saying really everything and x is equal to everything else, which doesn't have a name, but people don't study that, of course. And then the dependent types correspond to all morphisms when we take the path space to be x, or isomorphisms when we take it to be x times x. So that's the notion of dependent types. Okay, there's a nice example in cat. We can take path x to be x to the free isomorphism category. So this thing is just the category of isomorphisms in x. The objects are isomorphisms. The morphisms are continuum squares. And here in this example, dependent types correspond to isofibrations. People know what that is. And isofibration in category of categories is just a functor, where if you have an isomorphism in the base and a chosen lift of, say, the domain, then you can lift the whole isomorphism. Okay. In topological spaces, we can take path x to be, I learned this a few slides ago, gamma x to the more paths. For technical reasons, it's not exactly x to just interval, but very close. And here, as I said before, dependent types correspond to an array of its fibrations. In Kahn complexes, we can't do this really in simplest sense, but if we just restrict to the subcategory of fibrant objects of Kahn complexes, we can take the path space to be x to the interval. This depending object. And their dependent types might be kind of clear from this example that we should expect dependent types there to correspond to Kahn fibration. Of course, in all these examples are really things where you can lift paths with a starting point to a path. And indeed, you can generalize this really to any Szynski model category, and there the dependent projections correspond to just the fibrations in the model category, which would have a special name. Okay, so that's just talking about the identity type. But when we do type theory, there are other types around that we need to actually start talking about things, have enough expressiveness in our language. So to have pi types, we basically need that the category is locally Cartesian closed. And to have the universe, what I'm just calling type here, probably confusing, to have the universe type, we need a kind of classifying fibration. So these things don't work very well. They're not locally Cartesian closed, like this one, not locally Cartesian closed. Maybe that guy in general is not locally Cartesian closed. This guy doesn't have classifying fibration. And so our favorite model is really Kahn complexes with the topos, it's like everything you could want it to be. And certain of the model categories. And there are other models that people usually calling infinity toposes. Okay, so lots of models, but our favorite one, I think, is Kahn complexes. And I think really for what I'm going to talk about, if you don't know so much about Kahn complexes, you can definitely think of topological spaces. So times where it goes wrong is just very very infrequently and very technical. Okay, so now I want to talk about using homotopy type theory to do mathematics. And so I've just talked about this analogy, which I guess in many different ways can be made precise between types, dependent types, and fibrations. And now I want to talk about actually using homotopy type theory and why it's advantageous. Okay, so the univalence axiom characterizes identities in one particular type, the universe of types, which I'm just, again, just calling type with a capital T. So as Eric mentioned, we have this identity type, and for many types, like types that are built out of type formers, like for particular types that we're interested in, without assuming some axioms, we can't actually get a handle on what the identities are in that type. So we do know without any axioms what the identities are in the sigma type, but in everything else like the universe and the pi type, we don't have a correspondence between this kind of atomic notion of identities and kind of a familiar notion that we wanted to coincide with. So the univalence axiom identifies these two things. So it says that if we have two types A living in the universe of types, capital P type, then the identity type between them coincides with the type of equivalences between them. And so this is a kind of hand-built notion of a function from A to B and from B to A that Eric explained has intractable fibers, which is roughly the same as saying that the compositions in both directions are equivalent to the identity. So there with this axiom, we've kind of made sure that the identities in the universe coincide with what we think they should be. Equivalences of types, really homotopy equivalences of spaces if we look at interpretations into, say, Kahn complexes. Okay, and we can use this univalence axiom to characterize in the same way identities in other types. It's kind of make this axiom for one type, and then everything that we really could want follows from it. So in particular, if we look at a function space or function type from A to B, and we look at identities, between two functions f and g. The equivalence axiom implies function extensionality, as Eric already explained. And this means that the identity between two functions f and g coincides with saying basically that for all x, fx is identical to gx. Yeah.
Explain a bit more what is the difference between the blue symbol equivalence and the green one?
Yes, okay. There's not a big technical difference, but I guess I'm using green to mean like a type. So I'm saying that the symbol is like open parenthesis, blank, equivalence, blank, close parenthesis is a type forming symbol. So we put an A and a B in there, we get a type, the type of equivalences. And I mean, that's also true here for these blue symbols, but what I kind of want to use the blue symbols for is a statement that these two things are equivalences. So, sorry?
It is external to the.
So in actuality, they're exactly the same, but I want to read these statements as the green ones being internal and the blue ones being external. Okay. I mean, the thing is, in type theory, everything, but when we truly do type theory, everything is internal. Every statement we make, every proof we write is internal. Everything is really a mathematical object, not English.
I think so. For the blue one, she's not trying to just describe the type. She's trying to say she knows an element.
That's a good point.
When she says proposition and uses there's an equivalence with the blue, she's. I mean, it is the type of equivalences, but she's asserting that she knows an element of that. That's stronger than just writing the type itself.
Thanks. That's exactly what I should say. Yeah. So I want to use this sentence that this is equivalent to this, like as an English sentence, as an external sentence, that this is equivalent to this. If we think about this as this whole thing as being a type, we would say that there's a term of this type. Okay, so I want to say that the identity type from A to B, if we assert that the identity type from A to B is equivalent to the type of equivalences from A to B, then it applies these other things. So in particular, the identity type between two functions is the same as this pointwise identity between the functions. And then if we start looking at types of algebraic objects, we also get nice characterizations. So the equivalence axiom, basically we just kind of analyze what the equivalence axiom is saying for two types that happen to be sets. It's saying that the identity type between two types that are sets is equivalent to the type of bijections between S and T. So it's very satisfying, it's very good. If it were something else, we would be a bit worried. But we have structure results. So if we have some kind of a set with extra structure, like a group or a ring or something like that, we can form the type of those things, say groups. We can look at the identity type between two particular groups, and the equivalence axiom implies that that's the same as isomorphisms, that's group isomorphisms. That's we did on Danielson. And if we define categories in the correct way, then we also find that the identity type between two categories coincides with the type of categorical equivalences between them. Let's do the reciprocal and Schulman. And then recent work by some co-authors and I, in this work, we showed that this pattern we can generalize really to any algebraic structure, where of course we define what any means. And we might call these kinds of things equivalence principles. So this is really advantageous when doing homotopical mathematics, because for those of us who are familiar with category theory, know that restricting yourselves to talking about properties or constructions that are invariant under equivalence of categories could be kind of tricky. It's not totally obvious, maybe not as obvious as when you're doing group theory. And if you're doing like bi-categorical stuff or affinity categorical stuff, you get more and more tricky the higher you go at these kinds of levels. Okay. And maybe also I want to make the point that here this is just a statement about type theory, but when we interpret all this into, say, complexes, we get a space of categories, a space of groups. And there, the homotopies, the paths between categories or groups correspond to categorical equivalences or group isomorphism. So we want to do kind of homotopical mathematics, homotopical study of these things. We have exactly the correct recipe here. Okay. When should I end? Okay, thanks. Yeah.
With questions,
Okay, thanks. Okay, so I want to say, as I've said before, that with hot, when we have transport, we first of all have that everything is invariant under the notion of this identity, like the atomic notion of identity in type theory, and we add ambivalence that helps us identify identity with other notions of sameness that we're actually really interested in, like categorical equivalence or isomorphism or bicategorical equivalence or something more complicated. We put these together, then everything we can say, like every property we can write down, or every construction we can make respects not just the notion of identity, but the real notion of equivalence that we're interested in, like categorical equivalence or something. Okay, so in summary, let me talk about the advantages of hot as I see them. So first of all, first, as I haven't talked about at all so far, proofs in homotopy type theory can be verified by a computer. That's nice. As I haven't really talked about either, I think I've talked about a little bit more. We might say that hot is the theory of homotopy theory in the sense of like model theory logic. In the sense that if we do homotopy theory in the traditional way by just thinking about simplicial sets and trying not to do anything that's not very like a homotopy, it's kind of hard to tie our hands behind our backs by ourselves. But in the language of homotopy type theory, then we can only say things that are invariant under homotopy theory. So it's kind of the actual language that I think mathematicians have always envisaged when they use the phrase homotopy theory. But not just that, the results are of course valid not just in our favorite model of spaces, complexes, or special sets, but in all models. So in all these infinity compasses, which are becoming more and more interesting as we know more about them. Okay, and the third one, which I've tried to explain, is that we can study algebraic structures with homotopical tools. In particular, as I've said now a bunch of times, everything is invariant under the appropriate notion of sameness. Okay, so now I'm going to start saying something about directed homotopy type theory. And of course, the goal is to have a version of this, of the story I just told, where we don't just capture regular old spaces like complexes or in some sense topological spaces, but notions of directed spaces, of course, and maybe also categories and higher categories. Okay, so we talked a lot about transport, and that's because it's kind of the one thing that you are really trying to capture when you develop with directed homotopy type theory. So just as in homotopy type theory, everything respects identities. In directed homotopy type theory, everything should respect directed identities in a directed way. That's like the one thing here that we're trying to build a world around. Okay, so our first desideratum is maybe we want to be able to prove a statement like this, that for any dependent type, D dependent on a type A, and for every path from X to Y, and now instead of id for the identity type, I'm using hom, taking inspiration from like homomorphisms and categories, hom-sets. We have a homomorphism type now that's going to play the role of the directed identity type. So if we have a dependent type D and a path from X to Y, then we want, again, this to produce a function between the guide Vx and the guide Vy, the fibers of the fibration, but of course we want this to be non-equivocal. Okay, so in particular, you might think about cat, which is the nicest, most easy category of kind of directed things to understand. There's so much theory there already. So if we have a function, or a functor from a category D to a category A, right, so Now, try to do exactly the same thing as I did a few slides ago. We can think about squares like this, and they're liftings. And so this means that if we have not an isomorphism now, but a morphism in A, and a chosen lift of, say, the domain, then we can lift the whole morphism. Okay, so again, just like before, that's kind of just a shadow of a real property that we want, which is just kind of a more coherent version of that. Which is now, if we consider a functor from D to A, we can think about in some sense, the path space, taking the category A and raising it to the free arrow, not free isomorphism anymore, of course, and taking the mapping path space factorization, where this is now the category of, well, it's really a common category, I should have written it that way, but it's the category of pairs of an object in D and a morphism in A that starts at the image of the type. Okay, so if we have a lift, that is really just saying that if we have a path in A and a starting point in D, then we can lift the whole path kind of in a coherent way. That's the point of bundling them all up into one category. Okay, and so if we think about functors with this kind of property, that whenever we can make a commutative square like this, with this kind of thing on the left, there's a lift. These are exactly the retract closure of Grothendieck opfibrations. Yes.
Question. And then sorry, maybe you are going to talk about this afterwards. But so you want to lift into the future, right? Why don't you want to lift into the past?
Yes, I'm going to talk about that.
Okay, sure.
Yes, maybe it's obvious to everyone here, but I'm going to try to motivate that. Okay, so here's an example from rewriting of just the examples are going to be just very basic, just the basic kind of phenomena, or like just features of the language that we want to capture, or of these examples that we want to capture in the language. Okay, so let's consider maybe a particular dependent type. I think we saw this one in Eric's talk. Let's consider a dependent type like vect n, dependent on a natural number n. So vect 0 is going to be the type of just list of like 0, and vect 1 is going to be the type of list of like 1. I guess I'm leaving whatever the things are in the list, like the components implicit. But now, if we have a directed version of type theory, we could consider n not to be a set like we normally do, but a directed homotopy type with terms like, I know, not just 0, successor of 0 like 1 and 2, etc., etc., but the type with terms that represent all kinds of addition and stuff like that. And since we're doing rewriting, we might want to think about all the paths from that like +1 to 4, +1. Okay, so we have this. Here's an illustration of this. So we have this this directed path, this rewrite rule from 3 + 1 to 4, and the transport is just saying that if we have a type of vectors of length 3 + 1, then we should be able to coerce that, maybe computer scientific jargon, or transport that along this rewrite rule to vectors of length 4. That's just kind of the basic kind of thing that we want to capture in the language. So that's one example of transport. Here's maybe our favorite example of directed spaces for concurrency that we saw in Uli's talk. So here we have the Swiss flag. So everything, of course, everyone's probably seen this, of traces going from this initial state to this final state. And we have here the safe states and the unreachable states. And we can formulate notions of reachability and safety of the predicates on points in this space, or in terms of this type. So, for example, we can have a predicate reachability that basically says there is a directed homotopy from the initial state to our guy X. And of course, this should be able to be transported along directed paths. But like you pointed out, we also have other predicates like safety, basically saying that there is a directed path from our point or our state or our term to the final state. And this, of course, is not going to be possible to transport this forward that's not reflected in the intended semantics, but we can transport it backwards. We also want a notion of being able to transport things backwards. Okay, so I'm going to annotate now this colon with information about how we're thinking about this variable being used. So we are kind of, maybe we want to say that this variable is being used in a covariant way, or in a way that we can transport into the future, and this variable is being used in a contravariant way, or a way that we can transport into the past. Okay, but then of course we could talk about hom-XX. Maybe it's not so interesting in this example, but to, for example, talk about like identity paths, if we have to postulate, we need to be able to write down something like hom-XX. We want to use the same X twice. And in the previous slide, we saw that since X is there, it should be able to be transported forward. And since X is also in the first spot, it should be able to be transported backwards in some sense. But I mean, of course, we can't really do that because we have both these X's. They're kind of sometimes locking this type in. And so it can only be transported along invertible directed paths, of course. Okay, so we have another notion of the sense in which we want to be able to transport things just along invertible directed paths. And we also want to be able to express undirected homotopy. Like, for example, I think in this, this kind of stuff, we're always interested in looking at maybe two directed paths, say from the initial state to the final state, and wondering to what extent they themselves are homotopic in an undirected way. Which we also are talking about, in some cases, undirected homotopy and wanting to be able to transport along undirected homotopy. So we have these two new notions of transport, which I'm going to annotate with an X, for ones that can only be transported like almost never really, only along invertible directed paths, and ones that can be transported like always along all undirected paths. Okay, so we have now these four notions of transports. We have this really minimal one, contravariant, covariant, and maybe isovariant or equivariant at the top. And in both the settings of directed spaces and categories, we see, well, I've written three things there. They kind of generate these four things, these three levels. So in directed spaces, we're really interested in these two things, directed paths and undirected paths. There's also a derivable notion, which is the invertible directed paths. And in categories, we're really usually talking about these two things, isomorphisms and morphisms, but there's a third one that's directable, this localization. And so these two smallest notions correspond to the X, the directed paths and morphisms, depending on if you want to transport forward or backward, correspond to the minus and the plus, and the undirected paths and localization correspond to the zero. Okay, but unfortunately, there are even more notions of transport. So for instance, maybe our favorite dependent type, the one that like we really have to understand to get the whole thing going, is hom-AXY. That's dependent contravariantly on X and covariantly on Y. And now I'm going to maybe kind of brush over this. So this is kind of technical, but we want to be able to transport hom-XY along paths in X, backwards or forwards along Y, without disturbing the other variable, Y or X. And at least semantically, that's not very difficult, but we have to be careful about that. So in cat, if we take the discrete fibration of hom-sets, that's really, I mean, I shouldn't say the word discrete fibration, that's really a two-sided fibration, which is some categorical notion that goes back to substance to street. And so that's saying that we have these two projections, one to the domain, one to the codomain. And not only is this a fibration and this an opfibration, in the sense that we can lift in these ways, we can transport these ways, so that when we transport along paths here, we like the fiber, thinking about the fiber over this guy is not being changed. There's some here. Okay, so we kind of understand the situation in cat. And for longer contexts, so we can think we have something more interesting going on. We might have a context with 10 variables, all of which have different variances annotated on them. We have more complicated diagrams. We might have like 3 legs, or 2 of the legs might depend on one guy themselves, and so on and so forth. Okay, so in the last few minutes, let me talk about some progress towards understanding how all this stuff works. Okay, so I want to say that there's at least 3 things going on here. There's the syntax, the semantics. So the syntax is the type theory. The semantics is basically understanding fibrations in this really generalized sense, and the connections. So we need some categorical machinery, in particular comprehension categories, for those of you who might know what that means, to kind of connect these 2 things. And so they're all, none of them is completely done, but they're all getting there. There's also, of course, I mean, at some point we want to start thinking about formalization, so actually implementing the syntax into a computer, and like actual applications. So maybe actually saying something interesting about those examples of rewriting and concurrency that I talked about. Okay, so let me just say something about the actual approach here. I mean, hopefully it'll be kind of clear the way I describe the problem and the answer itself. So this is based on a paper from a few years ago. So in this like kind of first approximation to the syntax, we only focus on modeling kind of directed transport, and then the minimal transport, because we actually need that too to talk about directed transport, because we need to say like hom-sets sometimes. Okay, so to do this, we use operators and core that can turn any type into like the opposite type that has all the same terms, but where it has in the opposite direction, and core one that maybe in some sense removes all the paths, or just leaves the undirected paths, or sorry, the invertible directed paths in the directed topology sense. Okay, and then of course we want to use inclusions from T-core, the thing where we forget all the paths T, and also into T-op. And I'm just going to write down the formation and the introduction rule, and they look hopefully very familiar. So if we have an A and A op and a B and A, then we can form the homomorphism type between them. And we want to have an identity between A and A, and like I said before, we want this to be in the core, because we can always transport it along invertible directed paths. Okay, so instead of writing down the very complicated elimination and computation rules that are really much longer than the identity one, but are very analogous, we're just going to say that we have left and right ones, where for the identity type, we just have one elimination and computation rule. And so the reason why we have left and right ones is really just because we want to model, we want to capture forward transport along any homomorphism in A, and backward transport along any homomorphism in A op. And really we have this is the right one, this is the left one, and both of them collapse to, if you plug in something from A core, to be able to go in any direction along homomorphisms in A core. Okay, and there's a model in the category of categories that captures exactly what is suggested by the notation. So that's great. Okay, but there are some problems with this. That's why it's just the first approximation, first kind of toy syntax. So first of all, I want to say that I mean, the first problem is that we're only modeling these 3 notions of transport, backwards, forwards, and the really minimal one. And the other problem is that to capture all these different notions of transport, I'm really using kind of one notion of transport plus, and then kind of encoding the other notions by having this op and this core operator into that notion. And that works on cat, but you don't have these operators in really any other model of directed spaces or categories or anything. Like they don't even exist in 2 categories. So you might think that, of course, in any directed space, you can op the paths. You can just take the directed space with the opposite paths. But since we're really not thinking just about types, But about dependent types, what we're thinking of as fibrations, for that we have to like take a fibration of directed spaces and off each fiber, off the paths of each fiber without changing the paths of the base, which of course would be some paths of the total space. So that's not something that you want to get involved with, I think. So we want to be more sophisticated with our approach and not use those kinds of operators. So the second approximation, maybe I'll say this very quickly now, is to use the hom rules that we had. I think those are the correct ones. But to, instead of using this very unsophisticated encoding of the different directions, to have a more sophisticated one, for those of you who know what it means, a modal type theory, where we have 4 different kinds of dependency, as I was saying this before. And in particular, I mean, one reason why we were capturing the undirected notion of homotopy in the previous model is because it's just kind of one type theory. And if you have the identity type and the hom type, they would collapse to each other. And having these 4 different kinds of dependent types, you have sufficiently enough boundaries between things to prevent these 2 guys from collapsing into each other. And we have models in, or like the whole point is to describe a syntax where we have models in any category with the following kind of generalized weak factorization system. Okay, so let me talk a little bit about the semantics. This is joint work with Benno Vandenberg and Aaron Petoskey. So we saw before that models of the identity type are generated by a symmetric functorial path object. And the fact that this left part is in the left class of the weak factorization system and this right guy is in the right class is exactly what you need to have enough homotopical algebra to produce transport. And we want to emulate this situation, right, to get transport in our intended models. Okay, so in our intended models, what we have is something that looks more like this. We have a notion of kind of directed path space of all these hom types. And we have something that, at least in the example in categories, already has a name, 2-sided fibration. So we have these fibration structures of these 2 maps that have to interact nicely. Okay, I'm not going to explain this now, but we want to basically generalize the notion of weak factorization system to encompass this kind of thing, which looks very different than just 2 arrows. Basically, where the problem is really that we have like these different shapes. And as I explained a few slides ago, we don't just have this kind of shape, but we have more complicated things going on off here. We might have 3 legs or a kind of diamond, and we want to understand what it means for that thing to have kind of a transport structure or kind of fibration structure. Okay, and so we've done this, but I just want to say that in particular, the 2-sided fibrations studied in the 70s by Street in the theory of categories are captured by the theory, the same way that this notion of weak factorization system can capture the notion of isofibrations and categories I talked about before. Okay, so that's it. Thanks a lot.
Questions?
So you have an axiom of univalence of direct or
Yeah, so I think we want to have a like a fully functional type theory before we put axiom like equivalence in. But yeah, I mean, certainly we could, I mean, just right now say that the functions in the universe correspond to the directed paths of the universe. And I didn't talk about it in this talk, but especially in terms of like computational behavior, we're not, I shouldn't say computational behavior, but in the sense of getting nice theorems about how the type theory works that are interested computer scientists, like this is really important because we know all these things like naturality for free and stuff like that. Yeah, but first we want at least the homotopy part to start behaving correctly before we start thinking about universes.
Other questions? Yeah.
So a question about the last part about the two-sided vibration. So is that also captured in the syntax in the sense of equality?
Yeah, yeah. So what's happening here is that we, I guess, so in this story that I guess I studied very closely in my thesis, I characterized the like kind of path objects that produce models of the identity type. And so in this story, we can use like one path object and kind of derive all the notions from them. But really, what we're really doing and what this picture suggests is that you really have 4 different path objects that are going on, and that with these 4 different path objects, for any context, with any kind of annotations about all the variances, we can first like draw the diagram of all the dependencies, and then write the kind of required notion of lifting or of transport in terms of all the different path objects that are relevant for each type in the context. I don't know if that answers the question.
Yeah, I mean, so like, can you transport backwards in one direction and forward in another versus forward in one direction and backwards in the other? You get an equation. If you have like the home type, you have something on ID, and then you transport forwards along the path from B to prime, and backwards along the path from prime to A. Or if you do it in the other order, are those 2 things equal?
Yeah, exactly. Yeah. So that's exactly the kind of thing that we needed to capture, because you could certainly just say that, or kind of naively, you could try to say that if you have this kind of hom thing, then it should be, well, contravariant X, covariant Y, which suggests that there should be 2 dependencies on the type that you're looking at. One which is a fibration, like a contravariant thing, and one which is an opfibration, a covariant thing. But exactly what you're saying, like we need more structure to ensure that if we transport backwards, if we have 2 paths, one here from like X to X prime and one here from Y to Y prime, that if we transport backwards to X prime and forwards to Y prime, or the other way around, we get the same thing. So it's exactly the extra thing that's going on.
So is that something like, is that something we can prove, that equality inside give that as an axiom, or can you derive it from some other rule?
Yeah, let me think about that. Yeah, so we can show that it's the same up to this notion of equality, the smallest one.
Maybe direction of one. So you have different now structures of factorizations.
Mm-hmm.
One way to think of them in a kind of uniform way is to follow Lobir and to think of them as image structure. So typically, the identity path object is the image of the canonical predicate over X along the diagonal.
Mm-hmm.
That's Lobir.
Mm-hmm.
And this became part of the. So I was wondering here whether your factorization, which is, if I understand, factorization into spans, follows that kind of thing. And whether there is a kind of generic way to understand this path object.
Yeah, so if I understand what you're saying, if we look at the kind of path object that's produced by the diagonal, then it's this one. This one is the path object produced by the diagonal, the minimal one. So we could certainly choose, like, when we set up a semantics, we need to choose 4 different notions of equality. So we could certainly choose the diagonal one, say for this one. That's actually what I do. Where is it? In this model. I choose the minimal one, just to make everything easier. Or you could choose something that's more interesting and maybe natural from the perspective of a category theorist, but just to choose not the minimal one where you're looking at literal equality of objects, but of the notion of isomorphism. We're looking at isomorphism of objects. So yeah, so we definitely can capture that, but I mean, I guess the idea is that depending on the category that you're looking at and what you want to study, you can use different notions of paths.
Right. Yes. So in the end, it's about the notion of predicate.
Yeah.
Maybe a last quick question.
Yeah, you explained us that we can think of, we can use homotopy type to describe a model-independent homotopy theory. Is there something similar expectable for infinity categories?
Yes, I mean, everyone knows this is a very, very hard problem, so I don't want to make any promises, of course, because they're very likely to fail. But I mean, just like in homotopy type theory, we can iterate the identity type and have an infinity groupoid. I mean, here, at least in theory, we can iterate the hom type and have an infinity category. And so it hopefully produces the notion of an infinity category that, I don't know, maybe is a useful addition to the zoo of notions of infinity category. But yeah, I don't want to make any claims about that.
Yeah, I had similar questions and many others actually, but I'm fortunate enough that you stayed a little longer, so I can ask you more questions. So a bit late, I suggest that we carry on with Gregory. Maybe if you want to take a very quick cup of coffee, that's about time that Gregory is collecting.